Okay, time to see how to get that done. Not directory, Ludovic. Better. Okay. Do not pass that as shared. So here, it might be tricky at first to know how many variables in a real world scenario, how many variables you have to pass. The easy way to know exactly which variables you have to pass without analyzing the full code is just to put default none. Why? Because now if I try to compile, and I try to, I can't even, I was going to say and try to run, I can't even compile. It's going to tell me my thread ID is not specified in enclosing parallel. So now you know exactly which variables are going to be used inside your parallel region. The compiler does all the work for you. So we have three variables here: my thread ID, common array, and step. Okay. So my thread ID, how did you pass this one? Shared private or first private? Yeah, go ahead. Shared? My thread ID. Who thinks, that's great that there are multiple opinions, that's great. Who thinks shared for my thread ID, this one? Who thinks shared? Yes, okay. Who thinks private? Okay. Who thinks first private? First private, okay. Private or first private, they both work here, okay? Because each thread is going to have its own myThreadID copy variable, so you're good. The fact that it's initialized to whatever value was in it before, 0 or not, is irrelevant here. Why? Because the first thing you do is that you overwrite its value with that. Okay, so whether there was a value or not, it doesn't matter. It doesn't matter. You're going to overwrite it anyway. The one you don't want is shared. Because imagine just two threads, and we share this variable. I'm thread 0, I'm going to set it to 0. The other thread is going to rewrite it to 1. Remember, we're fighting on the same variable now. So whatever comes next here, I'm thread 0, but maybe that now has been set to 1. So me accessing this variable now is going to lead to very nasty, incorrect results. So yeah, you're right. Private or first private. In this case, I'll go with private so that I can save the initialization time in case there's any really. So my thread ID, okay. What about step? What do you use with step? Who says shared? Okay, who says private? First private? Okay. First private, yes. You can pass it as shared if you want, because you're just reading from it. But yeah, first private is definitely a very intuitive way to do it. Okay, final one, common array. Oops, sorry. For the common array, who says shared? Yes, private. First private. Yeah, okay, you're right. It's shared. We want all the threads to interact with that same array. Okay, that seems good. That seems okay. Okay, let's try to compile that. Ah, yeah, it's not the same name anymore. That seems good. 0, 0 plus 1 times 1 to 3, plus 2 times, plus 3 times. Okay, done. Again, didn't take much, but just need to make sure that we know which scope we're passing here. We have what? A little bit less than 20 minutes before the break. Oh, yes, Dennis. So here in this case, yes, step is a constant. So what I've seen is there are compilers that tell you, why are you even telling me it's a first private? Because behind the scenes, it's even removing this variable. It's just going to insert 1, 2, 3. And there are compilers, I think it was the Cray compiler that was doing this kind of optimization, and other compilers were fine with it. So they were saying, no, it's a variable, you need to tell me what you do with it. I must say, I don't know what's the stance of the OpenMP standard on this one. If you have to give it, I think you have to give it away, and then if the compiler somehow tries to remove it by optimizing the code, that's something else. But I have a variable, I need to give it away. So if there's an OpenMP expert in the room that knows or has seen this line in the OpenMP standard, feel free to tell me. Oh yeah, in case you were deluded to the point of thinking, I knew the entire OpenMP standard, not happening. I'm going to disappoint you, but no. 650 pages, no, I don't know that by heart. I may know 10% of the OpenMP standard pretty well. I may know 15, 20 more percent, rather good, but the rest is very, very, very tricky. So, okay, I can still start to work on the next one, the work sharing, and then we'll go to the break, and we'll do the exercise when we come back, and we'll resume from there. We're going to see two what we call work sharing constructs, single and master. Master is being deprecated. I'm just showing it to you so that you have an idea of a nuance there. Single, it's a new construct like parallel. You've seen parallel, now we're going to see single. What it does is, unlike parallel, where the associated structured block, the one between curly brackets, is executed by every thread, the code that is associated to a single construct will be done only by a single thread. Even if you have 5 million threads, only one of them, and no more, will do it. Which one? You don't know. And you cannot tell. It will be whatever thread happens to be available at that moment, which gives great flexibility to your code. There's what we call an implicit synchronization at the end, which we're going to start seeing as the next topic, synchronization. What happens is, we are 4 threads. One of us has been picked to execute that code. The other 3 are going to wait until that thread finishes, so then we can all resume execution, all 4 of us at the same time. Okay? Synchronization. If you want to see an example, all it takes is this little pragma OMP single, and you put your code, and that's it. In OpenMP, it's always one word at a time for you to do anything you want, really. Same for GPUs tomorrow. That's single. There's another one, which again is being deprecated, so it should disappear at OpenMP 6.0, I think, which is the master. So master thread is that only the master threads runs the code. Yeah, so far so good. Pragma OMP master. There is a very subtle difference between the two, which is when it's master is the blue arrow, by the way. It's always the blue arrow. The master, there's no implicit synchronization at the end. And that's a very mean question, but can you guess? Can someone come up with an idea of why single, when only one thread, we don't know which one, but one thread will do that code, there is an implicit synchronization at the end, but when it's master, so only one thread doing it, there is no implicit synchronization at the end. In both ways, in both scenarios, it's just one thread doing something, but one makes a synchronization and one doesn't. Is there anyone who can think of a reason why that is? Yes, go ahead. I think you're on the right track. Let's see if you have something slightly different to say about this. Was more or less the same idea? It's fine. Here, we're not closing the fork. When we use a single, we still have the blue arrow and the red arrows. We still have that. It's just that for a given portion of the code, we say, okay, just one of these arrows will do it, but we still have all 4 threads available. The other ones just don't do it. Yes? I think you're gravitating around the right idea. So what I think... Oh, yes, go for it. Oh, no, it doesn't have a special treatment. That was the idea. That could have been, but no. What I think happens is, from an algorithmic point of view, when you write your code and it's single, when it comes to the post conditions, it means what holds at the end of that single. You don't know which thread did that. Imagine that the single is updating the value of my copy, or something like this. You don't know which thread did it, so you cannot assume that you can tell which thread did it in the rest of your code if you have some branches on, oh, the thread that updated this can do this or something else. With master, you know exactly which thread did that portion. So right after, you can tell that the other threads, you know exactly which IDs they have, because they're just not the master thread. Now I had questions about, yeah, but what's the master thread? Like, which thread is the master thread? It's defined as the one that is running before you call parallel. So in my illustrations, it's the blue arrow. Okay, that's the master thread. So, simple now. Oh, yes, go ahead. So that's where a question that seems perfectly reasonable and that asks for a very simple answer, on my end, is less easy to answer. Why? Because, yes, that sounds absolutely reasonable, that sounds absolutely sensical and smart, but the standard, I do not think the standard says that the master thread has to be thread 0. But as far as I know, the compilers, basically the people who implement OpenMP, these compilers, kind of all agreed right away, let's put 0, 0, yeah, 0. So we all agree on 0, but technically I cannot say yes, because the PDF document doesn't say that as a rule. So that's where I have to, because if I say something wrong and I have an OpenMP person in the room, they're going to say, you don't know your stuff. Yes. Sorry, what did you do? Yes. Without... This is correct. Yes, but you're how to say while also remaining diplomatic. You're doing all these observations from a very rational point of view. Yes, it's the first one, it has to be like this, and it makes total sense, and I agree. But maybe 25 years ago, there were another understanding for something, and even the mapping of threads to cores, there used to be more exotic mappings. Because if you have cores from 0 to 4, or 0 to 3, you expect to see thread 0 on core 0, thread 1 on core 1, thread 2 on core 3, and thread 3 on core 3. But it's not always the case. You had, I won't give names because I don't remember, which is, they were starting from the very end. So thread 0 was on the last core, and then thread 1 was on the first core, and they were going from there. They had a reason to do it. I don't remember the reason, but it's like, it was not making sense, but they were still having a reason behind the scenes. So yes, master thread being always 0 is what you can assume to be the case. But if one day a compiler decides to just go full forth and fireworks and they say, no, my master thread has ID 3259, it's fine. It's compliant. So, yeah, indeed. Yes. Sure. Oh. Oh. Two questions here. You have two aspects here. The first part is there is a we are at two different abstraction layers here. A thread, what we're seeing here, is a virtual body, if you want. Okay, we create 5,000 threads if you want. Even if we have 4 cores, we can run 5,000 threads. They will just take turns on the cores. It's like your laptop. If you try to see right now how many threads your laptop is running, you will see it may be running 1,000 threads, but you don't have 1,000 cores. The way it works is a thread runs 1 or 2 milliseconds, then it's put to sleep. Another thread goes there for 1 or 2 milliseconds and put to sleep. And your operating system keeps doing that. So a given thread may not be on the same core forever. That's the first aspect. You're talking about hardware, what the hardware resources, but the OpenMP threads are at a different level. They may be mapped to multiple resources. The other part that you raise is something called heterogeneous computing, which is what happens if inside my node I have 2 CPUs but different CPUs. So different clock frequency, different RAM, different speeds. That gets tricky. I don't know how the decisions are made there, and how do you determine which core would be the most efficient. That's also, if you have benchmarking people in the room, they'll tell you that can be tricky to determine. In parallel programs, it's very hard to have estimations of predictability. So again, makes total sense, a very reasonable question, but I'm afraid the answer is more complex. Any other questions before we start the exercise? But I think we won't finish it. We'll go to the break in 5 minutes anyway, so we'll have time to correct it afterwards. No question? Okay. Well, then you have the next exercise. Okay, so we'll correct this one after the break. Spoiler alert, I might have been a little sneaky on this one. We'll see in the correction if you've encountered an issue and we're like, why this happened? Well, you'll see what I mean after that. Okay, well then, I guess it's 15:30, so 3:30. So feel free to slowly find your way into the coffee break if you want. If you want to ask me questions, you're more than happy. I will probably have a few comments to make about the returning mentors, what I've said this morning. So we'll do that maybe in 15 minutes, so we have time to get a coffee break. And those who would like to hear a few of my comments, feel free to come back before and I'll discuss. I don't want to take the OpenMP time away from you for my comments. So. Well, coffee time? Break time? No?